So in this video, we're going to be looking at exponential functions, just trying to get our feet wet with it. So you know how like with linear, you have y equals mx plus b slope-intercept form? Well, this is kind of similar to that, to where your exponential functions have a generic form that they go with. So here's the generic form here. So it's y equals a b to the x. So the a, that is kind of your starting or initial value. And then your growth or decay factor, that's going to be the b. So that's similar to like slope, except this is exponential, so it behaves differently. And then this x here, that's your number of times that the function grows or decays. And we'll kind of get into what that means a little bit later in the video. Now, you might also see it like this, a b to the x like this, where the b is in parentheses, because this might be it's a little bit weird because it's got the times dot there. Some people, they like the parentheses better, but it is multiplication. It's a and then times b to the x, okay? Now, linear is when you are adding the same amount. So that's y equals mx plus b. Now, exponential, these ones here, these are when you are multiplying the same amount over and over and over and over again, instead of like adding the same amount over and over and over again for each step or whatever. So quick example here, what is n? So we're going from 32, 64, 128, 256. There's the n there that we're looking for. And then there's 1024 there. So if we're looking at these numbers, they might be familiar if you've ever played the game 2048. Well, they are indeed in that game, and you've probably seen them before, at least the top few there. So let's look at the pattern here, right? 32 to 64 to 128 to 256. You're just multiplying by 2. These numbers are being doubled. 32 times 2, 64 times 2, 128 times 2. Guess what? 256 times 2, right? So in this case, that's the way we're going to figure that number out there. Okay, now this does follow that exponential form because it's repeated multiplication. So in this case here, we have y equals, and now when we go to like put this into the formula here, right? We're looking for this letter n. We basically already know what it is, 512. Okay, so here, so the a, that's your starting amount. Well, you got to look at 0. 0 is your starting amount on tables. Okay, 0 goes to 64. So the value for a, the number that replaces the a, is 64. Now our growth or decay factor, right? This is multiplying times 2. So that's our growth factor. It's a 2. Okay. Now, if we look here for this x here, that's the number of grows or decays. Well, that's over here. That's your input. So that's going to be replaced with a number 3. So the 3 goes there to replace that. So like on this one, we can go ahead and just figure it out. Oh, times 2 times 2 times 2. And then I take this number times 2 to get this one. But let's say there was a bunch of empty ones there and you're trying to find like one way down here, like number 100 or something like that. Then you might need to use this formula here. So we're just going over kind of another way of finding the same answer. So either way, it's going to be 512. Another example, after graduating from college, Brendan receives 2 different job offers. Both pay a starting salary of $65,000 per year. One job promises $5,600 raise per year, and the other one guarantees an 8% raise per year. So we're going to be filling out these tables here for the $5,600 per year versus the 8% per year. Okay, so here we go. We're going to start with the $5,600 per year. So year 0, how much is Brendan making? Well, he's making $65,000. Says so right there. That's what his starting salary. 0 is starting year, so $65,000 there. Now, after 1 year, right, what are we going to do? Well, it's going to give him a $5,600 raise for each year. So we just add $5,600 to the 65,000, and it's 70,600. Now that we're done, now that Brandon's done with year 1, now we're moving on to year 2, another raise of 5,600 or 5,600, and now we're at 76,200. Another year, another 5,600. Now we're at 81,800. Another year goes by, another raise of 5,600. So we're going to add 5,600 to the previous year, and boom, there's our next year there. So after 4 years, Brandon's going to be making $87,400. So if you see here, Brandon is getting the same amount raise every single year, or he's adding the same amount each year for his salary. So anytime you're doing this, adding the same amount each year, that's a constant rate. That is a linear function or linear relationship. So if we are going to put this in an equation, we would be thinking slope-intercept form, y equals mx plus b. So in this case here, his yearly salary, his y equals, right, it's going up $5,600 every year, T for time in years, and then it's starting at, so it's a plus, starting at $65,000, okay? So that's kind of the summary statement for what's going on up here. Remember, this is y equals mx plus b. M is your slope or your rate, and then the b is your start amount. Now let's look at the second job where Brandon is getting a raise of 8% every year. So in year 0, it's going to be the exact same amount, right? Year 0 is he's starting out, he's brand new, he's fresh, right? And then after 1 year, he's going to get that 8% raise. So remember, whenever we do calculations with percents, we change them to decimals, right? So we got to add in an 8 or a 0.08, okay? So and we're going to add to that the original amount, which is 100%. Okay, so in order to figure out your growth factor for this case here, it's the original amount, 100%, plus the 8%, 0.08. So 100% is 1, that's the original amount, plus 0.08 is 1.08. So that's going to be your growth factor there. So in this case here, we're going to take the $65,000 and we're going to multiply it by 1.08, and he's going to be at 70,200 for the first year or the year after he started. Okay, now again, he finishes that year. Now he gets to get another raise, another 8% raise. So we have the original 70,200 there, plus the 0.8, the 8% raise. So calculator time, right? There we go. 75,816. After that year, now he's moving on. Year 3, he gets another raise, another 8% raise, so multiply by 1.08. Now he's at 81,881 and some change there. And then after that year, his raise for the third year going into the fourth year, another times 1.08. So now he's at 88,431.78. So we can see at some point here, he ends up getting a better deal. He started out slower on this 8% raise, but you can see that it's growing what we call exponentially. So we're multiplying on this top one, we're adding the same amount, linear. So here we're multiplying the same amount. So that's going to be an exponential function. So that's y equals a times b to the x. Okay, so here we go. So remember, it's y times a, y equals a times b to the x, right? A is your start amount, right? You start at $65,000. And then the b, that's your growth rate. That's this number here, 1.08. And then the x, that's the number of growths that take place. So that's going to be t for time in years. So kind of a similar story, right? We have 65,000 for the start amount, and this is adding 5,600 every year, and this is multiplying 1.08 for every year there. So just remember, with these exponential functions, they will be written like this or like this, right? Starting amount is the a there or there, and then it's so the start amount times b to the x. So a, the starting amount times b to the x, where b is going to be that growth or decay factor. If it's getting smaller, that's going to be exponential decay, and then that x, that's the number of times it grows or decays. In the last example, it was number of years. Remember, when we have the exponential, that's where you're multiplying the same amount. That's the b there. Whereas linear, you got y equals mx plus b, right? The m, that is going to be the amount that you're adding for each year, if you're talking about like the last example with Brandon.